Students, welcome to this MOOC course on Advanced Analytical Technique. My name is Shahab Ali Asghar Nami and I am serving as Associate Professor of Chemistry at Department of Industrial Chemistry, Aligarh Muslim University, Aligarh. So we have started Unit 3 regarding chromatography, and in our previous lectures we have already covered chromatography, the basic principle, the underlying concepts, and then we move forward and we have explored the two important theories which govern the zone broadening, and those two theories were the rate theory and the plate theory. So we have already discussed that plate theory was a purely hypothetical concept given by Martin and Sinch, while the other concept, which is called as the rate theory, was based on Van Deemeter equation. So we are moving our concept of Van Deemeter and we are trying to quantify the column efficiency with regard to zone broadening. So let us delve into the subject again. So up till now we have analyzed these three terms, that is A, B upon U and Cu, and we have explored that how these terms actually govern the H, that is the HETP, height equivalent to theoretical plates. Now we have already discussed that for an efficient column, for have a best resolution, the value of H must be kept as small as possible, as low as possible. That is, the height of each theoretical plate, which is continuous plates residing in a column, must be as small as possible. And in order to have H as small as possible, the necessary condition is that A must be as small as possible, B upon U must be as small as possible, and Cu must be as small as possible, where we have defined that U is the velocity of the mobile phase. Now let us explore the specific terms, that is the A term, the B term and the C term on an individual basis. So A may be defined as lambda dp, where lambda is actually a function of packing uniformity and column geometry. For an effective separation or effective resolution, the packing, the uniform packing, that is the particles which are packed in a column must be uniformly packed and they must be as small as possible. Lambda also depends upon the column geometry, that which type of column you are actually using. Similarly, dp is the diameter of the stationary phase particle. So in order to have, because this A is actually the eddy current and it depends upon the random walk of the solute molecules, that is, it arises because of the difference in the distance covered by the solute molecules of the same molecule actually. So we have already discussed that because of the difference in the distance covered by each solute molecule, it gives rise to band broadening. So this dp is actually the particle diameter and alpha is a function of packing uniformity and column geometry. Similarly, the B term, that is the second term, is equal to 2 gamma upon dm, where gamma is the obstruction factor and it again depends upon the column packing. That is, if you have an effective column packed and it is the packing, that is the particles are as small as possible, then of course we have a best resolution. So this is how actually, and dm is the solute diffusion coefficient in the mobile phase. So A is with regard to multiple path length, B is because of the, that is equal to 2 gamma dm, gamma is again obstruction factor, and it actually depends upon the column packing. If you have a uniform packing, then its value is low. Similarly, with regard to C, it's actually, we know that it is the resistance. So in fact it is a combination of Cs and Cm, that is the resistance experienced by the solute molecules in the stationary phase and in the mobile phase. So if, for example, if your solute is having a very good interaction with the stationary phase, then of course Cs is going to, then the resistance will be high. Similarly, the opposite is true with the mobile phase. So this actually tells you about the resistance or about the equilibration which the solute molecules will have with the stationary phase and of course with the mobile phase. So this is how these three terms actually work, and this is the significance of the Van Deemeter equation terms, that is A, B and C. We are going to look these terms with regard to specific separations when we talk about the liquid chromatography and about the gas chromatography. So how these three terms, that is the A term and the combined B upon U term and the combined Cu terms actually comes into play, we will see in the coming slides. So moving forward, now let us draw a curve with regard to the HETP, that is the height equivalent to theoretical plate, and the velocity of the mobile phase. So if we draw a curve, then it look like this. If we plot H on the y-axis and if we plot U, then if we plot B upon U, for example, then B upon U can be plotted like this. Experimentally it is found this. Okay. Now with regard to Cu, we know that it is a combination of two things. So this can be drawn like this. It is Cs and it is like Cm. Now if you are going to make a combined curve of this is B upon U, if you may want to draw a combined curve of these three terms, then you will get H like this. You will get H like this. That is, at a certain point, if you drop a perpendicular, then at a certain point you will find this velocity is the optimum velocity. This is the optimum velocity, which we have talked in detail in our previous slides. So you can see that this is the H, that is called as the height equivalent to theoretical plates, HETP. So if you see that the left side is dominated by the B upon U term, while the right side is dominated by the Cu term. So this is the optimum velocity which is to be kept to have the best efficiency of your column. And the best efficiency means that you have your peaks must be well resolved. That in your chronogram you get a well resolved peaks. For example, if it is 2 component, you have 2 peaks, or if it is 3 component, you have 3 peaks, and so on and so forth. One, say first component, second component, and of course the third components. So it is again the time, and it is again the detector response. It is again the detector response. Okay, so this bottom point tells you the optimum velocity, and this actually tells you the HETP. And HETP and the length of the column are related. We know that N is equal to L upon H. So greater the number of theoretical plates, better will be the efficiency. Or similarly, you can say that greater or larger or longer the length of the column, greater will be its efficiency, or you can say greater will be its resolving power. So for example, in HPLC, the optimum velocity is found to be 1 ml per minute. We are going to explore these features in our coming slides. So practical optimization. Now we have to practically, this Van Deemeter equation is very helpful to us. For example, when we are dealing with certain systems like GC or HPLC, then we have to select the best speed so that we can have a better resolution. For example, in GC, the velocity of the mobile phase must be somewhere lie between 25 to 30 centimeter per second. Similarly, in HPLC, which is an advanced GC, this ranges to 1 ml per minute. So you can see the difference. So what we have to do, we have to avoid very high this velocity, because if velocity is very high, then the Cu term will be very big, and if Cu term is big, then H will increase, because we know that H is equal to A plus B upon U plus Cu. So if you increase the velocity of the mobile phase, then this term will increase, which will increase this H. And if H increases, then your column efficiency will be compromised. So we have to keep an eye that about the velocity. If it is low, then definitely this term will rise and it will create more diffusion. It will create more diffusion. Diffusion will be high. Diffusion will be high. And this actually happens in, such case happens in GC. We are going to see this. Okay. So let's move forward with this information. Now in gas chromatography. In gas chromatography, the dominant term is actually B upon U. Now let us see what happens to the Van Deemeter equation. The Van Deemeter equation, H may be defined as A plus P upon U plus Cu. Now in gas chromatography, your mobile phase is always a gas, and we know that when the solute, which is in GC, is a volatile compound, when this volatile compound mixes with the carrier gas, what happens is that all the molecules are now in the gaseous state, and the gas has the highest diffusion, and the diffusion is so high that this term becomes dominant, and this term, this A, actually becomes negligible. It becomes negligible or very low. It becomes very low. Now because of this, the Van Deemeter equation in terms of gas chromatography, it becomes H is equal to B upon U plus Cu. Because now there is no random walk. There is no random walk because your solute molecules, which were actually volatile in nature, it gets mixed with the carrier gas and the diffusion is very high. So this diffusion, and we know that diffusion is very high, so this factor becomes dominant. And at optimum speed, you will get sharp peaks. Okay. So a common example is the volatile organic compounds, VOCs separation, for example, the separation of benzene and toluene. So in gas chromatography, you have to remember that it is the B upon U term which becomes dominant and A becomes negligible, or it can be ignored. Okay, it can be ignored. So let us move towards the liquid chromatography. Now here our case actually changes. What happens is that in liquid chromatography, now your mobile phase is liquid, unlike the gas in the gas chromatography. So here actually the dominant term becomes, now let us write the Van Deemeter equation again, A plus B upon U plus Cu. Now here this B upon U becomes negligible because now this mobile phase is liquid, and for example your substance which is to be separated into its constituent is also a liquid. So the diffusion in liquid is very small, and because the diffusion is very small, you can neglect B upon U term. So in terms of liquid chromatography, your Van Deemeter equation effectively becomes H plus Cu, and here the dominant term is Cu, that is the mass transfer, and again it involves the equilibration of the solute molecule with the stationary phase and with the mobile phase. A very good example is the chromatography of various drug compounds, where we have to ascertain the formulation of certain drugs, certain excipients, and of course we have to check the impurities also. So this is how your equation, or the Van Deemeter equation, takes this shape or takes this expression. Okay, so let us have a comparative table where we have summarized all our parameters, and we are looking at in terms of gas chromatography and high performance liquid chromatography. So here the broadening occurs because of the longitudinal diffusion, that is here the B upon U terms becomes dominant, while in HPLC it is the Cu term. Similarly, with regard to the flow dependency, or you can say velocity, in GC it is high, it is to be kept high, while in HPLC it is to be kept moderate. Now diffusion coefficient, that is the dm, in here is 10 raised to the power of 5 minus 5 meter square per second, while in terms of HPLC it is further low. So what happens is that in terms of, if you thinking in terms of your velocity, then in GC you have to keep the optimum flow towards the lower side, while in the HPLC you have to keep it in the middle of that is in the middle of low and high. So you can see that the equation is all the way same, that is H is equal to A plus B upon U plus CU, but you have to decide the utility of this equation on your chromatographic technique basis, that is whether you are using GC, whether you are using HPLC, or whether you are using liquid chromatography, because in every type of chromatography the different parameters, some parameters become dominant and some becomes negligible. Okay, so real life example, pharmaceutical analysis. For example, we have already discussed an example where we have taken paracetamol and where we have checked the different impurities present in it on the basis of the peaks occurring in it. Okay, so that can be checked. For example, if your system is pure, then definitely you will get a single peak, and the area under the peak will give you a qualitative idea that how much drug is present and how much you have specified. So it gives you an idea, that is, it gives you a qualitative idea about the excipients, and also a quantitative idea about the amount of drug present. And the optimization can be done by using the Van Deemeter equation or Van Deemeter plot. That is, to have an effective resolution, we should have a sharp peak with controlled bandwidth. Now if the bandwidth, if it is like this, that is, it tells you that it may contain two peaks. So you have to have effective or sharper peaks to ascertain the purity of your drug or of your sample. Now another example is the assessment of air quality. For example, we can check various pollutants, the presence of various gases like sulfur dioxides, like nitrogen dioxides, and other nitrogen compounds in air by running our sample through a environmental gas chromatograph, where we can check the pollutants in air. We can check certain organic compounds like benzene and xylene, which are very harmful. Similarly, we can tune our column, we can tune our flow rate so that to have a better resolution. And a better resolution means that there must be two things which are to be satisfied. First of all, the peaks must be as separated as possible, that is the distance between them. For example, it is the distance between them, so this distance should be as large. So this delta Z must be as large as possible, number one. And number two is that this peak width, it must be kept as low as possible. We are going to derive a relation between this W, if you say it is W1, and if you say W2, we are going to derive a relation between this delta Z, W1 and W2 in our coming slides, so that we can actually quantify our column performance with regard to different peaks, okay, which our detector responds or senses. Okay, so what are the actually important thing which we have to bear in mind? For example, ultra high performance liquid chromatography uses small particles of the order of 2 micrometer, and because of this it gets a good number of plates. And as we know that as the number of plate rises, that is the column length increases, and as the column length increases, the you can say resolution increases, that is RS, or you can say the column efficiency column efficiency also increases. So you can see that the moment you actually make your particle small, then of course small particles will have a better packing, and if the packing is better, then eddy current, or you can say the eddy diffusion, can be minimized. Okay, so your column efficiency increases. And the best example which presently we are using is the microfluidic chips. Now these chips are actually so good with regard to separation that it can tell you, for example, with a 1 m, or you can say 1 nano liter sample, it can tell you the whole story. For example, if you have a blood sample, it can tell all the parameters coming into it. For example, it can tell you about the hemoglobin concentration, it can tell you about the platelet count. So many, you can calculate the so many parameters just by a very small drop of blood. So that is how actually this technique is sensitive and sensible and reproducible. Now, what are the advantages of using this Van Deemeter equation? Number first, that it predicts, the Van Deemeter equation actually predicts your optimum flow rate. So you don't have to run a number of columns just to fix your flow rate, but just by calculation by using, that is the equation, H is equal to A plus B upon U plus Cu, you can just ascertain the optimum flow rate, that is the U. Similarly, it also lets you tells you how you have to design, because this is actually comes here, that is the lambda. Similarly, B it also tells you about the, because B is equal to 2 gamma or dm. Okay, so these parameters, that is the lambda and gamma, tells you about the column design, that which type of column you have to have, so that you can have an effective separation, so that you can have a very good column efficiency. Now these are very advantages in cases of GC, HPLC and CE also. Okay, so let's move forward. Of course there are certain limitations also. Now this Van Deemeter equation actually talks about the steady state conditions, that is your mobile phase is steadily moving across all those imaginary plates or theoretical plates whose distance you have specified by h. So these steady states does not actually exist in such a way practically. It neglects the temperature gradients, which are again very important, and these are not valid for open tubular columns. This fact we are going to recheck when we will study the gas chromatography. So these are the limitations, but of these limitations there are so many good things that Van Deemeter equation actually gives you a quantitative idea about the zone broadening. It gives you a quantitative idea about the zone broadening. It also gives you a quantitative idea about the distance between the peaks. So this theory actually is based on the experimental findings, and this Van Deemeter comes under, again I am telling you, it comes under the rate theory. So this comes under the rate theory, and rate theory actually uses the concept, it uses or utilizes the concept of plate theory. That is the concept of HETP, and of course the concept of number of equivalent plates. So this experimental theory is in fact based on the theoretical theory proposed by Martin Sinch. So let us summarize what we have covered up to this point of time. Number one, zone broadening actually reduces the resolution. Zone broadening, if your peak is broad, then it restricts your qualitative as well as the quantitative estimation of the different components present in the sample, present in the mixture. So zone broadening actually reduces the resolution, or it actually compromises your qualitative and the quantification of your analytes. Similarly, efficiency can be measured in terms of the number of theoretical plates and the height equivalent to theoretical plates. We have already discussed it, and there are so many equations. For example, n can easily be calculated by L upon H, where L is the length of packed column and H is equal to height equivalent to theoretical plate. Van Deemeter equation explains broadening cases. So it gives you a qualitative idea. Now optimization, we have to do optimization because optimization is a process which is going to improve our analytical performance. So the next talk will be based on the optimization of our column. So what is the takeaway message from our talk? That separation science is actually an art. It's an art of balancing diffusion, of balancing the flow of mobile phase, and of course establishing an equilibrium between the stationary phase and the mobile phase by the solute molecules. And all the tribute goes to the genius of their time, that is Martin and Singe, who actually proposed this plate theory in 1941, and they earned a Nobel Prize. They were bestowed by a Nobel Prize in 1952 for their separation theories. So this is how actually the band broadening actually gives you an idea, and Van Deemeter gives you an answer in terms of quantitative manner. Thank you very much for your patience listening. Thank you.